Okay, here for number 16, we have kind of a long one where we're going to balance a redox reaction. And we're going to do it in basic solution. Our first place to start is with oxidation numbers, because this will help us keep track of how the electrons are moving in the reaction. So I've written here our list of suggested oxidation numbers, where alkali metals are +1, alkali earth +2, fluorines -1, hydrogens +1, oxygen -2, and halogens are -1. And they're written this way in terms of increasing strictness. So alkali metals are the most demanding. They always have their +1 oxidation state. And anything below them, if need be, will be more flexible so that alkali metals can always be +1, and so on. So what we're going to do is go up to our reaction and look at what atoms we have. So here in this first set we have chlorine and we have oxygen. Both of these have suggested oxidation numbers, but we're going to assign for oxygen first because it's higher on our priority list. So we're going to give the oxygen its preferred -2 oxidation number. We have 7 oxygens, so they're going to overall contribute a -14. Our molecule is overall neutral, so we need all of the oxidation numbers in this to add up to be 0. So that means the chlorines need to contribute a +14. So that means our oxidation state on each chlorine is going to be -7. Or I'm sorry, +7. Okay, now we move on to H2O2. So hydrogen's higher up on our list. We're going to assign it +1 for an overall +2. This molecule is again overall neutral, so the oxygen is going to have to contribute -2, which means each oxygen is going to be -1. Okay, then we continue to the ClO2-, and again, oxygen's higher on our list, so we're going to give it its -2. There's 2 of them, so they're going to contribute -4. Our molecule has an overall charge of -1, so that means the chlorines need to contribute only +3. There's only 1, so it's going to have an oxidation state of +3. And then here we have O2, and it's just 1 atom, and the whole thing's neutral, so it's just going to be a 0. Okay, so we've done the first step of assigning oxidation numbers. I'm going to go ahead and erase the parts on the bottom, because we just care about the individual atoms' oxidation numbers. And now we're going to look for what changed. So we can see that the chlorine went from +7 to +3. And then we can see that the oxygen here went from -1 to 0. Okay, so now we can split into half reactions. So first up, we can take our blue reaction, where we have Cl2O7 being converted to Cl2-. Okay, so let's think about what kind of reaction that is. We have the chlorine going from an oxidation number of +7 to +3, so it's becoming more negative. So this is going to be a reduction because the ClO2 or Cl2O7 will have gained electrons. So the thing is if we look at the chlorines themselves here, they're not balanced on an atomic level. So I'm going to put a 2 there to make sure we have the same number of chlorines on both sides. Okay, so now if we look at the oxidation number, each chlorine went from +7 to +3. So each chlorine would have gained 4 electrons. But here we have 2 chlorines involved because of this 2 and this 2. So we would have had a total of 8 electrons transferred. Okay. So now we have our electrons accounted for, our chlorines match up, but our oxygens definitely do not. You can see we have 7 on the left and 2 on the right. And so the way we can add oxygens to the reaction is to add waters. And so here I'm going to add 5 waters, which gives me my 7 hydrogens, or I'm sorry, my 7 oxygens on the right to match the 7 on the left. But in fixing my oxygen problem, I've created a hydrogen problem, because now I have 10 hydrogens on the right and none on the left. So what I'm going to go ahead and do is just add 10 protons. Okay guys, I'm sorry, I'm going to have to amend what I did a little bit because I forgot to count for my 2 here. So over here, when I was looking at my oxygens, I have 7 oxygens on this side, but really I have 4 on the side, right? Not 2 like I was saying. So the difference is only of 3 oxygens, so I'm only going to need to add 3 waters. Sorry about that. Okay. You got to be careful counting your atoms. So now, my hydrogen problem, I have 6 hydrogens on the right that I need to account for. So I'm just going to add 6 protons here. And now that's balanced. And if we look at the atoms, it's balanced. And if we look at the charges, it's balanced too. So here I have on the left +6, -8. So overall I have a charge of -2. And then on the right I just have a charge of -2 overall. So they match both in terms of atoms and in terms of charge, which is important. And that's actually what had tipped me off that I made a mistake last time, so you can use that to check yourself. Okay, so we've balanced our first half reaction. Now let's go ahead and do the oxidation half reaction. So we have hydrogen peroxide reacting to form O2. And so if we look at the oxidation number on the oxygen, it's going from -1 to 0. So it's becoming less negative, which means it's giving off electrons. And so here we have 2 oxygens doing this in each. So we're going to be giving off one electron per oxygen, so a total of 2 electrons. Okay, our oxygens are balanced, so now we just need to figure out what to do with the hydrogens. And pretty simple, we're just going to add 2H plus to the right side. So now we can see that our atoms are balanced and our charge is balanced between the two left sides, because this side's neutral and this side's overall neutral. So now that we have each half reaction figured out, we have our reduction half reaction, we have our oxidation half reaction balanced, we're going to combine them. Okay, and so some things are going to cancel in this process. But if we look at this, our electrons aren't going to cancel. And the most important thing when we combine these reactions is to make sure that our electrons cancel. Because we aren't just going to have electrons floating around, and there's no way to scoop electrons into a reaction, really. So we're going to have to multiply the bottom reaction with the multiplier of 4 to make it so we have the same number of electrons in each reaction for them to cancel. So I'm going to go ahead and say we're going to have 4 hydrogen peroxides, creating 4 O2 minuses, which will then give off a total of 8 electrons into solution. And then we'll have 8 protons. And so now that we have our electrons canceling, we can look at the rest of the equation. And so the protons from up here are going to cancel because we have less of those there, and we'll end up with 2 protons in our products. And it looks like these 3 waters are going to cancel, and we'll end up, oh, I'm sorry, water and hydrogen peroxide are different. Okay, it looks like that's all that cancels. So now we can combine. Man, right? Okay, so now we have a balanced redox reaction. So the only thing is, now in this problem, they're asking for us about what happens when we're in basic conditions. And we can see here that we're not in basic conditions. We have extra protons floating around. If we were in basic conditions, we'd have excess hydroxide. So what I'm going to do is go ahead and just add 2 moles of hydroxide to both sides. Okay, and we know from all of our work with acid-base chemistry, these are going to combine to form 2 moles of water then. And then we can add those together to get 5 total moles of water. So our official, complete, overall reaction in basic conditions is going to be where we have 2 hydroxides with 1 Cl2O7 with 4 hydrogen peroxides react to form 4 moles of oxygen, 2 ClO2s minus, and then 5 total waters. Okay, so it asked us for the coefficient in front of hydroxide, and it's going to be 2 then. Okay, so these are quite a process, right? Just take it one step at a time and check in with yourself along the way. Make sure your atoms are balanced and your charge is balanced. And if you get to the end and it's not making sense, what I recommend is just starting over, trying again, because sometimes it can just be more work to look at it and try to catch your mistakes and scribble and fix things than to just start fresh, start clear, and then I think you'll have more success that way. Okay, and it is worth practicing these because even if you've done them a bunch, it's just easy to look at something the wrong way. You saw that. You saw me do that. So please get some good practice in. Okay, here we're talking about phosphoric acid, and it gives us the 3 different Kas for this. And whenever I see all the different Kas, what I like to do is write the dissociations that correspond to each one. So I've done that down there below. And now we can address the different statements there. So they say the weakest conjugate base involved is the PO3 or PO4 3- species. So I didn't write them in explicitly here, but the first Ka is going to be the largest of the 3 because H3PO4 hasn't lost any protons yet. It's willing to give them up. But if we have HPO4 2-, it's already given up 2 protons. It's not very excited about giving up another one. So it's going to have the smallest Ka. So if HPO4 2- is the weakest of the acids, then that means this is going to be the relative strongest of the conjugate bases. It has a 3- charge. It'll be pretty good at picking up protons and reforming those conjugate acids. Okay, so the first one's false. Okay, for the second one, it says both HPO4 2- and H2PO4- are amphoteric. So just remember that amph means both. And so that means they can act as both an acid and a base. And we see that this is true, right? In the case of here, H2PO4- would be acting as a base. It's the conjugate base there. But down here, it's acting as an acid. So it's doing both. And then we see the same kind of deal for the HPO4 2-. In this scenario, it's acting as the conjugate base, but then here, it's acting as the acid. Okay, so that's true. And then 3 we've already sort of addressed. The HPO4 2- is going to be the weakest of the acids because it's already given up 2 protons. So H2PO4, which has only lost 1 proton, is going to be stronger. So that one's out. So the answer here is just B. Here we have a reaction between perchloric acid, which is a strong acid, and lithium hydroxide, which is a strong base. So I'm just going to write, we have a reaction of H+, because we have a strong acid, with hydroxide because we have a strong base. And these are going to react and form water. The lithium and the perchlorate are going to be spectators, so we don't need to keep track of them. They're not going to have any effect on pH. And so since we have a reaction, we're going to go ahead and use our ICF table. For ICF table, we need moles. So we can do liters times our molarity, which is moles per liter, to get out moles. And so I'll do that to get the moles of H plus and OH minus. And I've written those into the table. So now I'm going to look and see which is the smaller number of moles. And then we can just work our table and look at what has the fewer moles, and that's going to be the proton, so that's going to get all used up. And we'll use that much of the hydroxide. And we really don't care about water. So we'll be left with 0.00295 moles of the hydroxide. So that's going to be the only thing in solution that affects our pH. And so we need just then to get our concentration of hydroxide, and then we can figure out pOH and pH. So we're going to take our moles and divide that by our total volume. And so our total volume is going to be the combination of both solutions. So it's going to be 27 mils. So we're going to divide it by that in liters, which is going to be 0.027 liters. And that gives us a hydroxide concentration of 0.109 molar. We can get pOH by taking the negative log of that. And it ends up being 0.96. So to get pH, we'll just do 14 minus 0.96, which is going to equal 13.04. which corresponds to answer B. Here for number 19, we're trying to get the pH of a salt solution, and the salt, strontium nitrite, is going to completely dissociate into strontium ions and nitrate ions. So we have to identify these ions as acidic or basic, and we can think of strontium as having come from strontium hydroxide. Strontium hydroxide is a strong base, so this is not going to affect pH. That's going to be a spectator. NO2 minus, we can think of having come from HNO2, which is a weak acid, making NO2 minus then the conjugate of a weak acid, which means the weak base. And we can figure out its concentration by saying if I have 0.1 molar of the salt, my concentration of nitrate is going to be 2 times that, because for every one of those salts I get 2 nitrates. And so now I'm going to have to say I have NO2 minus in solution, and it can react with water, and it's basic, so it's going to steal a proton off of that water. And leave behind hydroxide, which will then be our key to pH. And so we can go ahead and ice this out. So we're starting with 0.2 molar NO2 minus. Don't care about water. We don't have any of these to start. You can go ahead and say minus x, 0.2 minus x, plus x, plus x, x, x. And here we have a base reaction, right? So we're going to need a Kb to describe our reaction. But if we look up at the problem, they give us the Ka for the conjugate. And so to figure out Kb, we're going to have to use that rule where Kw equals Ka times Kb. We're at 25 degrees Celsius, so we can say 1 times 10 to the negative 14 for Kw, divided by Ka, which is 4.5 times 10 to the negative 4th, is equal to Kb. And when we solve that, we find that Kb is equal to 2.22 times 10 to the negative 11th. And then we can set that equal to our equilibrium expression of aqueous products over aqueous reactants and plug in our E line. So we get x squared divided by 0.2 minus x. Our K is small enough that we can ignore minus x. And then we can solve for x by multiplying by 0.2 and then taking the square root of that value. And we get that x is equal to 2.11 times 10 to the negative 6 molar. And if we look up at our ice table, we can remember that this was telling us about our hydroxide concentration. So when we go ahead and take the negative log of that number, we get our POH, which is 5.68. So our pH is going to be 14 minus that. Which is 8.32. And this makes sense because we started with a basic salt, so it should be greater than 7. That corresponds to answer choice B.